Hello, good morning, everyone. Welcome to today's CA webinar. So my name is Yao Yao, and I'm working in the CAN automation, and I'm today the speaker for the webinar. So at first, some information for joining the webinar. Please mute your microphone during the presentation. And you can use the chat function to place questions. And yes. Then at first, let me introduce myself briefly. And since 2016, I have been working in CAN automation, and I'm mainly responsible for the working groups CAN FD and CAN XL, and also for several working work groups for the higher layer of the CANopen FD. So from the working in the group, I have collected some knowledge about this field, and therefore will give you today a short introduction. Before we go to the main part of the webinar, so firstly, a short introduction of CAN automation. So for the audience who don't know us very well, and CAA is the international users and manufacturers group for the companies who develops and supports CANopen and other CAN-based higher layer protocols. We are founded in year 1992, and we provide CAN-based technical, product, and marketing information. We are located in Nuremberg, Germany. So here you can see the development of the CA membership now in actual 2021. We have about 700 members. And here you can see the CA history milestones. One important event is also relevant for the topic today is that the second generation CAN data link layer, CAN FD, was first time introduced on the 13th International CAN Conference in year 2012. And another event is in year 2018, CA and our members, we have started to discuss the third generation of the CAN-based data link layer as CAN XL. CAN XL has larger payload and will also be transmitted with higher bitrate. So if you are interested about it, you can inform it on the CA website. So now you can see the CA technical groups organization, and for the CAN FD, the documents are prepared by the interest group lower layers. In lower layers, we have several task forces and special interest group. So the topic for today, several task forces are related to the topic today. For example, the signal improvement, timestamp, commode choke, cable, and the other special interest group, they are discussing now, for example, CAN XL and a subset of CAN FD, the CAN FD Lite. This is a new, this is a subset of the CAN FD protocol. Is communicated of master-slave communication scheme. And we are discussing the EMC requirements for the new CAN XL transceiver. So the CANFD documents are also prepared by this interest group, formerly named, the group named also IG CANFD. Now the group's name is IG lower layers because we are discussing not only CANFD and also the other lower layers, for example, CANXL. So if you have any interest to participate in our working group, so we are welcome any proposal and comments for our documents. So if you have any feedback, you can contact us or send us an email. So CA services, we provide so technical and marketing informations for the system designer and device manufacturers. So with our publications, with our specifications, and we provide also events like this webinar and international CAN conference. So the international CAN conference, we have planned it last year originally, but because coronavirus, it cannot be took place. So this is now postponed to this year and will be and will take place between June 14th to 17th online. So everyone can participate this event, and we have already updated agenda on our website. If you are interested or for it, you can visit the website for the actual program. So which benefits would you have if you become a member? So there are some for some advantages for device designer and system designer. So you can, for example, get all actual specifications and documents, and also you can participate in the working group. You can network. You can you can network with other experts from other company, and communicating in the CAN community. And the history of CAN. So what we discussed today, the CAN FD. This is published as the ISO standard 11898-1, the classical CAN KFD data link layer in 2015, and also the part 2 specifies the improved high-speed physical layer, namely the CAN transceiver in 2016, and then the conformance test plan are also released as ISO standards. So now we go through the main topic. What is CAN-FD? So I think some of you already know. To remind, CAN-FD data frame can be transmitted with 2 different bit rates. In the arbitration phase, the bit rate depends on the network topology and is limited to 1 megabits. In the data phase, the bit rate is limited by the transceiver characteristics. And also the payload is up to 64 byte long and not limited to 8 byte anymore. So to achieve a robust communication and the higher bit rates, the system designer should consider the impact of the physical layer. So how can the system design impact the communication, and why should we discuss the system design? So one reason is that higher bit rates can bring the network closer to the physical limits. Therefore, the rules and recommendations need to be more strict. For example, towards higher bit rates, the symmetry becomes more and more important. If the transceiver is very asymmetric, it can lead to that the recessive bit is extremely shortened or lengthened compared to the nominal bit time. So this will cause bit error. And another reason is that higher bit rates need more strict bit timing settings in all nodes. CANopen is so the physical layer in classical CAN networks. So regarding the bit timing settings, tolerances are allowed, but for CAN FD, so when using bitrate switching, in order to achieve interoperability among devices, the system designer should take care that all nodes apply the very same bit timing settings. So of course, if you don't use the bitrate switching function, the bit timing settings can be set as in classical CAN. So the last issue is that for a KFD device, the ISO 11898-1 defines the bit timing requirements, and the ISO 11898-2 specifies the transceiver characteristic. But both standards don't provide any system design recommendations. The previous CIA interest group, CAN FD, has been discussing this topic since years and has released several parts of the CIA 601 series. These documents provide CAN FD node and system design recommendations and guidelines. So now we move to the next slide and see a typical issue of the network design. So now the figure you see shows the sampling of a recessive bit. So normally the sampling of a recessive bit in a transmitting node is more critical than the sampling of a dominant bit. So you can see the recessive bit is extremely shortened and delayed. If it is sampled at a normal sample point, you will get dominant instead of recessive. This figure shows the most important factors that lead to this delay. They include the three parts as the figure shown. The bit asymmetry can be introduced by physical layer components. System designers should select components with minimized asymmetry values to guarantee a functional and robust CAN FD network. The bit asymmetry should be as small as possible. Another important effect to lead this delay is the signal running effect. The running effect could cause an unstable receiving signal. To avoid this problem, CANopen FD document provides recommendations and guidelines to help node and system designer to establish a robust CAN FD communication. So then let us see what the CA601 document series provide. So on this slide, you see this document list. Part 1 provides some useful information about the transceiver loop delay symmetry, the bit timing symmetry, and the transmitter delay compensation. So this document explains how to interpret the parameters given by the ISO 11898-2 document. And part 2 specifies interface between the CAN FD protocol and the host controller. Part 3 recommends the bit timing configuration and some optimization hints for the physical layer. This includes a recommendation for the topology and for the device design. And the fourth part is now under review, in which the CAN FD transceiver with signal improvement capability is specified. Depending on the network topology, this technology enables data bit rates up to maximum 8 megabits. So the working group at the lower layer is now discussing to update the recommended parameter, the maximum supported longest propagation delay. So the new version is now under the final reviews and will be expectedly released soon this summer. And part 6 specifies the mechanical and electrical parameters for cables to be used in CAN FD networks. Last year, CA has released the above-mentioned documents as draft standard. Normally, the documents of the status draft standard are only accessible for CA members. Now, CA provides also non-members to subscribe the DS documents so that the CAN FD technology can be used more and more and to promote this technology. So one newest released part is the CA 110 document. This specified the parameters of common mode chokes to be used in classical CAN networks and CAN FD networks. And this is mostly used for automotive applications. And this document have the status draft standard specification. So and this cannot be subscribed. So the part 5 is still under development. This part will provide CAN FD reference topology examples. CA and some member companies are working on this topic, but currently the discussion has slowed down because of the COVID pandemic. So if you have requirements for CAN FD network topologies, or you are working on this field, you could contact us for further information. So we are glad if interested parties can join the working group, and every proposal and comments is welcome. And then to understand better what is the CAN FD device and system design, so we take a look at the physical interface layers according to the OSI reference layers. As shown in the figure, the CAN physical layer can be divided in 3 sublayers. So on the right side, you see you see the according standards that cover the sublayers. One of the important issue of the CAN FD system design is the setting of the bit time. Then we take a look at the bit timing setting. So at first, we see now the definition of the bit time. So 1 bit time is specified as 4 non-overlapping time segments. Here on the next slide, you can see the 4 segments. Each segment is constructed from an integer multiple of the time quantum. The time quantum as the smallest discrete timing resolution used by a CAN node. So the length of the time quantum is generated by a programmable divide of the CAN node's oscillator frequency. So 1 nominal bit time is minimum 8 time quanta and maximum 25 time quanta. So the bit time is selected by programming the width of the time quantum and the number of the time quanta in the various segments. So this has to be done in the CAN controllers. As said, 1 bit time consists of these 4 segments. The SIC is used to synchronize all the CAN nodes in the network and is always 1 time quantum. So the sample point is a specific moment in time defined as a percentage of the bit time. The location of the sample point is defined at the end of the phase SIC1. So the signal level is mirrored once per bit and at the sample point. So it is very simple. In order to make sure that a network is robust, it shall guarantee at the sample point the signal levels shall be stable, whether dominant or recessive. The parameter SJW stands for synchronization jump wise. As a result of resynchronization, phase SIC1 may be lengthened and or phase SIC2 may be shortened. So the amount of the lengthening and the shortening are given by this SJW. In principle, if the sample point is at the very far end of the bit time, the maximum possible network length can be achieved. Sampling earlier reduces the achievable network length, but synchronization jump-wise value is increased, so that it increases the robustness. The bit timing configuration has 2 aspects. One is the setting of the nominal time quantum for the arbitration phase and the data time quantum for the data phase. The other is the setting of the sample points, including the secondary sample point in the data phase when the transmitter delay compensation is used. So a CAN FD device shall fulfill the following requirements. at first, the first one, so CAN clock frequency, shall be used the 80 megahertz, and so here is a failure on my slide. Sorry. So for the CAN clock frequency, 40 hertz, 80 hertz, and 116 megahertz are recommended to use because they are all multiple of the 40 megahertz. So then it can simplify the setting of the bit timing. And then you should set the time quantum of the data phase and the time quantum in the so the time quantum in the arbitration phase is the same as in the data phase. And in all CAN FD devices, the same the sample point for the nominal bit rate shall be placed at 80% of the nominal bit time, and in or so for the data bit rate shall be placed to the same position of the data bit time. And the transmitter loop delay compensation shall also be activated. So this slide shows for the CANopen device, for the CANopen FD devices, but it is the same for the CAN FD devices. So this is an old slide I forget to update. Sorry. So except the above mentioned requirements, the CA 601-3 document recommended some bit timing settings as shown on the slide here, and I will not introduce them in details. You can find the explanation to the points in the part 3 document. Besides the bit timing configuration recommended in the part 3, so part 2 provides also important recommendations as the number of bit timing registers to be implemented. This figure here shows the theoretically possible CAN bit timing configurations in the data phase. The figure shows two eyes. The small eye represents the possible bit timing settings with the minimal configuration ranges required in the ISO standard. And the large eye represents the possible bit timing settings with the CAE recommended configuration range. The ISO standard requires smaller register is not sufficient for some bit rate combinations of the arbitration bit times and the data bit times. According the recommendation in part 2, part 3 lists or configuration or configurable data bit rates as shown in the figure. So this figure shows also the data bit, so the bit, data bit rate ranges for different CAN clock frequencies. If you use the higher layer protocol CANopen FD, so you can take a look in the CA 1301 document. So this document specifies the allowed bit timing setting in two tables. The table 7 specifies the setting for arbitration phase, and for data phase, the setting in table 8 can be used. So we suggest you to read the CA 601 document part 2 and 3. This can help you to understand the meaning of the parameter in the table and to make your setting easier. And the part 3 documents, the part 3 document provides also a Excel sheet. It can help to evaluate whether your data bit timing setting is functional in the system setup. So, so far, I talked about the bit timing settings. Now we see this figure of the recessive bit sampling again. One of the important factors that lead the delay of the dominant recessive edge is the signal running. So then we will take a look at this effect. The first question is how is the signal running generated? So running is caused by the reflections on the communication voltage wave because of impedance mismatch caused by, for example, undominated steps or branches in CAN network topologies. In classical CAN, the signal running is already exceeded, but it's not very critical because the bit times are long enough to allow running to dissipate. But with the higher bit rates in the CAN FD network, because the bit rate is increasing, therefore the bit time is shortened and the bit decision timing is shortened. So while the signal running time is as the same as in classical CAN. Therefore, it is difficult to establish a robust CAN FD communication in the network which has much signal running. And for proper functionality, it is necessary that occurring reflected waves do not suppress the dominant differential voltage levels below 900 millivolt and do not increase the recessive differential voltage level above 500 millivolt at each individual CAN node. So to relieve these effects, system designer have to limit the complexity or the size of the topologies. CIA has established the task force signal improvement to discuss the technical technique for a transceiver with signal improvement capability several years ago. And in 2015, CIA has released this document 601-4 version 100. In the meantime, different technologies are being developed. Therefore, CA started the discussion again, and there are two concepts for signal improvement are discussed. One technology is to suppress the running on the critical receiving nodes, and other one is to suppress the running on all the transmitting nodes. The last CAA 601-4 version 200 is released in year 2019 and provides the specification for the transceiver with signal improvement capability function. So in which the parameters as asymmetry as specified as similar as in the ISO 11898-2 document. And the actual version is also implementation independent. Now this document is under review again. the specification for the SIC is not changed. So the group is only updating the normative recommendation in the annex. And for the system design point of view, the range of the recommended supported longest propagation delay between any two nodes is changed to guarantee the robust communication. And an Excel sheet will also be released together with this document, and to help the implementer to calculate the numbers by yourself. And at the end, if you require higher bitrate or your network topology is not so optimized, you can choose to use this CAN-SIC transceiver. So on the next slide, we will see how the CAN-SIC transceiver works. So here we can see what the SIC transceiver can do. This is an example of the different behaviors of transceivers with and without the signal improvement capability. The signals are the differential voltages of the receiver input. The signal above shows the transceiver behavior without SIC. You can see much ringing at the state transition from dominant to recessive. And RxD2 is an example of a potential behavior of the signal with ringing. So the voltage overshoot exceed 500 millivolt can cause dominant glitches on RxD. And RxD3 shows worst case lengthening of dominant states. So some transceivers might filter out the recessive undershoot and extend the dominant level on RxD. And so in comparing, the signal below shows the behavior of the transceiver with signal improvement. So RxD1 illustrates this preferred and improved behavior. In generally, the SIC function can change the network impedance to drive actively the signal to recessive. Thereby, CAN-FD, the CAN-SIC transceiver, provides also a much tighter asymmetry performance. And in addition, in the document 601-4, we recommend also the maximum supported one-way propagation delay. And as shown in the figure, this is the delay between any two nodes with the maximum distance network-wide. The supported one-way propagation delay is calculated based on the specified timing behavior. As a lower bound signal improvement time and the transceiver asymmetry. This recommendation depends on the highest supported arbitration bit rate. So you can see in the curves, and but it is fully independent of the data bit rates. The new version will include an Excel sheet to help the implementer to find the proper combination of the maximum bus length and the highest arbitration bit rate. So you can change your setting in the Excel sheet and to generate the these curves by yourself and find the proper setting for your network for your setting. So using this CAN6 transceiver can bring significant benefits for the CAN-FD network design. So the newest experiences of simulation and tests show some new results. And as for the networks validated at 2 megabits with the high-speed CAN transceivers, and will generally operate at 5 megabits with the CAN6 transceivers, and potentially faster depending on the topology. So networks operating at 5 megabits is now a realistic proposal for network designer to consider, where previously this was limited to point-to-point connections. And depending on the topology, data bit rates up to 8 megabits can also be considered. So the CAN-FD SIC transceiver can also be used in the future technology. And in this topology example, the CAN-FD SIC transceivers can be used with the CAN-XL controllers for the ECUs. And this example is for automotive applications with 8 control units and a total line length of 10 meters, and is already tested in the lab. And the combination of CAN-SL controllers and CAN-FD SIC transceivers is possible. This means CAN-FD SIC transceiver can also be operated with CAN-SL protocol. So for this next generation data link layer CAN-SL, and for the compatibility of CAN-FD and CAN-SL, so we provide also for the webinars and also will be presented by experts from CIA member companies on the International CAN conference. So if you are interested on it, you can take a look on the CIA website. Besides the CIA 601 series, CIA specifies also the CAN time stamping in the CIA 603 document. And you can get more information in the paper of Mr. Florian Hartwig, provided in the 16th International CAN Conference. This part 6 of the CIA 601 series is recently released before 2 years, and this provides some parameter recommendation for cables using CAN-FD network. So like cable impedances should be within 110 ohms to 140 ohms, and PVC cables are not suggested. The PVC cable are very sensitive to temperature, so it can lead to the reducing of the impedance of the cable and a higher propagation delay. The impedance change can create a large impedance mismatch, and so generate ringing effects in the network. And but in relative simple networks, PVC cables may be considered, but it is highly recommended to cross-check the performance of the specific cable to be used over temperature. So the recent released the document CA 110 specifies the requirements and test methods of the mechanical and electrical parameters of commode chokes to be used in classical CAN and CAN networks. So the EMC requirements compliance with the IEC 62228-3 standard. For example, the maximum stray inductance shall be 500 nanohenry in the frequency range from 100 kilohertz to 10 megahertz. And also specifies the parameters like the capacitance between pin 1 and pin 3, the saturation current and the rated current, etc. So besides the recommendation for cables and for commode chokes, and in the CA 601-3 documents, you can find also some hints how to optimize your network. So for example, it is recommended to use always components qualified for higher bit rates, even if for 2 megabits CAN FD networks, 5 megabits qualified chips should be chosen. And you should use a linear topology and terminated at both ends, and reduce the total bus lines, limit the number of CAN nodes, and avoid long not terminated stubs, which are branches from the wire terminated CAN lines, and use stubs of centimeter range instead of meter range, and consider a high termination of not terminated steps. So and so on. You can find this hint in the 601-3 document. And with specifications and documents, so the CAN FD system design for higher bit rates is still a difficult topic. In principle, to judge if a network is working, a network simulation is normally required to check all cases, or to test the network even in the lab. The CAN automation organizes Plugfests as a service for CA members. The purpose of this CAN FD Plugfest, for example, is to prove the interoperability of the CAN devices, CAN nodes, which implement the CAN FD protocol. So also for the new development, the CAN FD, the CAN SIC transceiver, the interoperability is also important. The correct communication between the nodes with the CAN SIC transceivers from different manufacturers should be guaranteed. CAA is planning such CAN SIC transceiver Plugfest. So now we are waiting for hardware which should be available from semiconductor manufacturers soon. So here you can see the photo of the preceding CAN FD Plugfest in Detroit 2016. So the topology as shown is the variant harness testing of fault. So to sum up the speech, the robust CAN FD physical layer system designs require to respect more rules, and each system design needs to be validated individually. And so if you are interested in the reference topology for CAN FD, And so you can contact us and join our working group. So any proposal and comment is welcome. So if you have any questions, you can write in the chat, or you can also write an email to us. So my colleague and I will answer the question as soon as possible. And take a short look in the next CIA webinars. So the next highlights are the webinars on June 17th on June 16th and 17th. So these are the set programs of the International CAN Conference. So CIA is inviting experts from member companies as Bosch, Infineon, and NSP. So they will provide the latest information for the development of CAN-XL. And also you can subscribe to CIA's email services. And also information for you, CIA is planning to attend exhibitions next year. So we expected that would be possible again and can talk with you personally. If you have any questions, you can also write your questions to our service email address. So we will answer you as soon as possible. Okay, I see a question. So to the oscillator frequency, I read that 10, 20, 40, or 80 is required. It is only for CAN 2.0 or also for CAN FD. In principle, this is also for it is also for CAN FD, and it is not required. It is recommended. 20 megahertz, 40 megahertz, and 80 megahertz are recommended because 20 megahertz multiple with 2 is 14 and multiple with 2 is 18. So if you have your setting, your bit timing setting in the network in CAN nodes, and you can simply change the setting with the factor 2. So this is the reason why we recommend this frequency. So it is not required. This is only recommended. But I think for CAN FD node, 10 megahertz is a little low. So you can read the document 601-3 for more information that is described very in detail. Okay, thank you. And then I think we close the webinar today. And thank you for listening and join the participants, and see you next time.